Hello, and welcome to Chapter 9, Section 3. It's the last section of this chapter. Today we are looking at hypothesis testing for population means. So if you remember from the confidence interval chapter, there were two different ones that we could do, either a Z confidence interval or a T interval, because depending on what type of standard deviation you were given, that's how you determined whether you used a Z star or a T star. With hypothesis tests, same thing. We can either do a Z-test or a T-test for a population mean. So depending on the standard deviation given to you, you use a Z-test when you are given a population standard deviation. So this will sound something like they had a previous study done. Sometimes it's called like a pilot study. So some kind of study was done before. They found the standard deviation to be whatever. So that's considered a population standard deviation. A t-test is used when you are given a sample standard deviation or when you have to find your own standard deviation from a sample. So the wording of this, they might be talking about a sample at some point, and then the mean and standard deviation were blah and blah. And so that's them telling you from this sample, the mean that we calculated was this, and the standard deviation was this. So that would be from a sample. All right, so our hypothesis test process, we have our phantom process, so we want to be able to do that with our population means as well. So I want to do an example together, and then we'll talk a little bit more. So in our example, we have a classic rock radio station. They claim to play an average of 50 minutes of music every hour. However, it seems that every time you turn to the station, there is a commercial playing. Ugh, the worst. To investigate the station's claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of the 12 hours. Here are the number of minutes of music played during each of these hours. And then they list the data. Do you have convincing evidence that the station's claim is too high? So remember, we were talking about anytime they ask for like convincing evidence, do you have it or do you not? That means you're doing a hypothesis test. So let's start our phantom process. So the first thing we want to do is look at the parameter that we're trying to find. We're trying to find the true mean number of minutes of music played in an hour. So we want to make sure we include, the context of the problem when we talk about the parameter, whether it's a mean or proportion that we're talking about, and this entire section is just means. So, it's going to be a true mean. So the next part of our phantom, I just realized I tried to spell pantom instead of phantom, forgot the H. All right, so hypotheses is the next part for our PH. So hypotheses, we are trying to write our null hypothesis and our alternative hypothesis. So here, because we're dealing with a population mean now, we need to be using the symbol mu, because mu is the symbol that stands for population mean. The sample mean would be the x bar. And remember, we never use symbols for a sample anything in our hypotheses. So never use x bar, always mu. Okay, our null hypothesis, we always use the equal sign. So we are looking to see what the claim was in the problem. So the classic rock radio station claims to play an average of 50 minutes every hour. So that's the one we're using. If you calculate a mean from the sample, that would end up being a sample mean, and you can't use that number in your hypotheses because you're not hypothesizing about a sample. The whole point of the hypothesis test is that you're trying to see what the population mean is. There's no reason for you to make a hypothesis about a sample. If it's just a sample, you can just calculate your own mean and standard deviation, and there's no reason for you to do a whole hypothesis test about a sample, because just calculate it yourself. There's no reason to be guessing what the sample mean is. So 50 is going to be the number that we use. And then for our alternative hypothesis, do you have convincing evidence that the station's claim is too high? So we actually think that the station's claim is too high. So if 50 is too high, then we must be thinking it's smaller than 50. So I'm going to use the less than symbol. All right, so we're done with the hypotheses. The next part, so I've talked about last video how I know phantom is spelled P-H-A-N-T-O-M, but it makes more sense logically to name the test before you check the conditions for that test. So I usually go like phantom, whatever. Name the test for this one. So here we need to figure out if this is going to be a Z-test or a T-test, because based on the standard deviation that we're given, that's the one we're going to use. We are not giving a population standard deviation. They gave us a sample. with data, so that means we can calculate our own mean and standard deviation. So if we calculate our own, that's definitely from a sample then. So this will be a one sample t-test. For a population mean. Alrighty, so we've named the test. Now we can check our assumptions and conditions. So remember, we have the 3 every time. We need to check for the randomness, a random independent sample, and then we also need to check for normality. Okay, so in this problem, they did tell us that we randomly selected 12 different hours. So our sample is consisting of like different hours and how many minutes of music was played during that hour. So we know that we have a random sample of 12 different hours that was given to us. Independence, we can check for independence by using that 10% rule. And so if we look at the population, if a sample is just, different hours and the number of minutes it was being played, then the population would be like all the time that this radio station could be playing music. So we know the 12 hours that we have in our sample is less than 10% of all the time that a radio station could play music. All right, lastly, we check for normality. So our sample size is 12, so we don't have a large enough sample size to use central limit theorem. Remember, for means, we can't use the large counts rule because n times p, n times 1 minus p requires a proportion of some sort in order for you to use the large counts. So here we have to use central limit theorem, or the CLT, but we don't have large sample sizes, so central limit theorem would not apply. But we are given a data set, so we can graph this out and make sure that the distribution of the sample is not extremely skewed and there's no outliers. It can be a little bit skewed. It doesn't have to be like exactly normal, but we just are looking for no extreme skew. So I made a box plot with my data set in my calculator, and I'm just doing a rough sketch of it here just so the reader can see this is what it looks like. So as you can see, it's not extremely skewed. We can see it's a little bit skewed because the right end is a little bit longer than the left. But again, there's no extreme skew, so this is fine. You can also make a histogram and just do a rough sketch of a histogram here, just so the reader can see again. But one or the other, box plot I like because in the calculator it shows you automatically that whether there's outliers or not, because it'll calculate it for you, versus a histogram, it'll be more obvious because you'll have that gap, but it's just nice to be able to know for sure whether there's outliers or not rely on visual cues. So we will say that our distribution has no extreme skew or outliers, and we can proceed. So now we've named the test, we've checked for our assumptions and conditions. Now we can actually find our test statistic. So we said earlier that this was a t-test, so that means we are finding a t-score. So the formula for this is going to be the sample mean minus the mean of the population that we think it is, divided by the standard deviation of the sample over the square root of n. So kind of like the standard error part. All right, so in this sample, I got a sample mean of 47.917. The mean that we are using for the population is 50 because that was the number in our hypotheses. And then our sample standard deviation was 2.811 over the square root of 12 because I had 12 data points in my data set. All right, so this comes out to be negative 2.57. Okay, so our next step is to calculate our odds, or the p-value. So since this is a t-distribution, remember it's like kind of flatter than a normal distribution, but semi same shape. So our t-distribution has a mean of 0, standard deviation of 1 again. Our t-score was negative 2.57. And our original alternative hypothesis was that mu was less than 50. So we're trying to see like numbers that are going to be smaller than this as well. We also said normally you shade away from the mean. So the whole definition of a p-value is that it's what we observe to be extreme or more extreme than what we observed in our sample. So that's why it's always shaded away from the mean. So that's the area that we're trying to look for. If you have the table only and not a calculator, this is still doable even though the table itself only tells you like t-scores or like t-stars and not the actual probability itself. With a calculator, it's easier. So normally with a normal curve and not a t-distribution, we would calculate probabilities using normal CDF in our calculator. So that would be second vars, and then number 2 would be normal CDF. But we are trying to use a t-distribution, so instead of normal CDF, we're going to use t-CDF. So for me, it's number 6 down here, or you can just press the number 6. So it still asks you for the lower and upper just like the normal CDF would, but then it asks you for degrees of freedom instead of the mean and standard deviation. So you have to use your t-score of negative 2.57. And we are shading to the left, so our lower could be like negative 100,000, which was already input here for us, and then negative 2.57. Degrees of freedom, if you remember, is our formula of n minus 1. So our sample size was 12, minus 1 would be 11. Paste. Enter one more time. So there is our p-value right there. So 0.013. I'm going to write this out as the probability of t being less than negative 2.57 is 0.013, because this makes it look nice rather than just saying like this is the p-value 0.013. But here it makes it, look more mathematical. It makes us seem smarter for a grader to look at. And we've come across this issue in the past as well when we did the confidence intervals. We noticed that t-stars were different sometimes between the calculator and the table based on the sample size, because the table didn't always give you the most accurate degrees of freedom. Because as you got larger in your sample size, then the table didn't include every single value of a degree of freedom. So in general, anytime you use a t-score, we always want to list out what we're using as the degrees of freedom. So just make that into a habit. We use degrees of freedom of 11 here. Whether you use the table or the calculator, you still would have used 11 for your degrees of freedom because 11 is on the table. But get into that habit so that there is no question about what you used. In the future, there is a big difference. When we start getting into slightly more complicated hypothesis tests, the degrees of freedom will change a good amount. So that's why we want to make sure we just get into that habit of listing it out. Okay, I also wanted to show you how to find a p-value in the table, just in case, God forbid, your calculator dies during the AP test. Then at least you kind of have something you can use. So the table, we calculated a t-score of negative 2.57, but remember, whether your your t-score is positive or negative, it's kind of like that critical value. Your table will only tell you the positive ones. So we are looking for positive 2.57 to kind of compensate for our negative t-score. 2.57 as a t-score, we are looking in the middle of the table, but then using a degrees of freedom of 11 still. So we're basically looking at that one row right here. So the numbers that are closest to our 2.57 as a t-score would be right here, in between 2.328 and 2.718. So if you look up, it'll tell you the tail probability. So remember the table tells you like the tail probabilities on either end. So even though our t-score is negative, this will still work. So we know our p-value, the area on the ends, is going to be between 0.02 and 0.01. So this kind of makes sense too, because when we calculated it in our calculator, we got 0.013. So our p-value is going to be between 0.02 and 0.01. So using the table, it's not going to tell you the exact p-value, but you know what it's going to be between. That way, when we make our conclusion, we can still decide whether or not we should be rejecting or failing to reject the null hypothesis. All right, so finally we are at the step where we make a decision or state our conclusion. So this is the same format that I used last section when we talked about the proportions. The conclusion is going to be the same every time. We just need to fill in all our blanks. So our p-value of, so we got a p-value of 0.013, or if you use the table, you would say our p-value is between 0.02 and 0.01, which is less than or greater than alpha equals, okay, in this problem they didn't tell us, so we get to choose. Let's use 0.01 today. Okay. So 0.01, remember this kind of like goes with a 99% confidence. So if we're going with super confidence, then we also need a really low p-value in order to make sure we can reject our null hypothesis. 0.013 is greater than 0.01. So we don't get to reject today. So we fail to reject our null hypothesis, which means that there is not convincing evidence that. And then we go back to our parameter, the true mean number of minutes played on this radio station in an hour. Is less than 50. So again, just so we kind of talk about this again, when we fail to reject our null hypothesis, this means that we're not saying our null hypothesis is true, we just didn't have enough evidence to say that we could reject it. So here, we're basically saying that we don't have enough evidence, is not convincing evidence, that it's going to be less than 50 minutes per hour. So we don't know that for sure. All right, so there is our full phantom for this hypothesis test. So for a true population mean, the one sample t-test, we've got the full phantom, all the steps. I want to talk about one more type of hypothesis test today, which is pretty similar to what we just did. It's just the wording of the question is going to be slightly different because this is going to be a matched pairs t-test. So if you remember way back when we first started talking about experimental design, matched pairs was one of the experimental designs that we talked about. Matched pairs was when you had sets of data that were paired together that were really similar, or subjects that were very similar to each other, like twins, or even when the same person was used as like a before and after type of data collection. So that's when matched pairs would exist. All right, so an example. SpongeBob and Sandy are at their local bargain mart ready to pay for their items, but they wondered which lane was faster, the express lane or the regular lane. So obviously Sandy, being the scientific one, wanted to do a study on this, collect some data. So she's going to randomly select 10 different times to go to Bargain Mart, and then she's going to buy the same item each time. She's got to go with SpongeBob at the same time because one of them is going to use the express lane, the other is going to use the regular lane. They're going to flip a coin each time to see who's going in which lane so that it's randomized. And then they're going to enter the lanes at the same time, pay with the same method, and record the time in seconds that it took them to complete the transaction. So here's their data. All right, so this is a matched pairs t-test because we are looking at their data each individual time that they go into the store. It's going to need to be paired together because if the store was busier at a certain time versus another day, then that matters. So that's why we have to compare the regular lane and the express lane on each of those days separately. So the question we're trying to answer is there convincing evidence that the express lane is faster on average? Which makes sense. The express lane is called express, so it should be faster. So in order to calculate these, this matched pairs t-score, all that good stuff, we actually need to deal with just one set of data because right now we have two. We have all the data for regular lane and all the data for express lane. But because we are matching this together, we want to really then look at the difference between each of these times. So what I've done is in my calculator, I have entered all of my regular lane data into L1 and all my express lane data into L2. Because then in L3, I can really quickly have my calculator find the differences between each of these times. So if I do L1 minus L2, and make sure you're scrolled all the way up to L3 before you start typing this in. When you hit enter, it'll calculate all the differences for us. Look at that, beautiful. So really this set of data, these differences, is the set of data that we're using then to calculate our sample mean and our sample standard deviation. So this is our sample data. I also want to point out, because I'm ending up with some positive and some negative differences here, this means that because I subtracted L1 from L2, regular minus express, that means if express is supposed to be faster, then the numbers in the express lane should be smaller than in the regular lane. So when I subtract this way, ending up with a positive number means that the express lane was a smaller number, which means faster. So like these instances where I have negative numbers, that means the express lane was actually slower. Okay, so keep that in mind because when we write our hypotheses, we need to make sure which direction we subtracted from. So following our phantom process, we have our parameter is that we are trying to find the true mean, but this time it is the difference. Because it's matched pairs, we're always looking at differences now. And that's why we made that third data list of just differences. So we are looking for the true mean difference in seconds that it took for them to complete the transaction. Next up is our hypotheses. So with our hypotheses, because we are looking at a true mean difference, we are using mu, but then we're also going to use a little subscript d to stand for difference. That way our readers know like this is what we're talking about when in our hypotheses. So mu subscript d, oops. So our null hypothesis is going to have the equal sign. And so because we're talking about a difference, and when we do the null hypothesis, we're always saying that there's no difference. If there's no difference, then the difference between our data sets should be 0. No difference, difference of 0. Okay, so our alternative hypothesis then, we're still using 0 as our number. We're saying that the express lane should be faster. That's what we believe. So if the express lane is faster, that means when I subtract my regular lane from the express lane, I should end up with a positive number in order for the express lane to be the smaller of the two numbers. So I'm going to say the mean difference should be greater than 0, a positive difference. All right, so next we name the test. This is a matched pairs t-test. Our assumptions and conditions, I'm going to go kind of quickly through this. We have a random sample of times that were selected to go to the bargain mart. The 10% rule, 10 is less than the 10% of all possible times that they could go to the store. And then lastly, to check for normality, we have a small sample size, so CLT does not apply, which means we're going to have to make a graph. So using our calculator, second stat plot will take me to the graphs that I want. I'm going to make sure it says on. And I'm going to make a histogram this time since I did a box plot in the last example. And remember, for your X list, this time we are looking at our differences. So that means we need to look at L3. Okay, so I'm going to quit and then zoom 9 so everything fits nicely. There is my graph. I'm going to do a quick sketch on my paper, and then obviously no extreme skew, no outliers. Fantastic. So finally, we get to calculate our test statistic. So the formula looks like this. It's basically the same formula that we had before. I just put little subscript d's there so that we know that it's like the mean, the difference of the mean, the standard deviation of the differences, and so on. So in our calculator, when we calculate this out, stat calc, one of our stats, we want to make sure we are using the L3 list again because this is supposed to be where all our differences are. So we get a sample mean of 28.4, sample standard deviation of 66.56. And our population mean would be 0 because that's what we used in our hypotheses. I forgot what number we used. 66.56. And our sample size was 10 because we had 10 differences in our list 3. Okay, so then calculating this out, I get a t-score of 1.349. So now when we find our odds, we are looking for the probability that t is going to be greater than 1.349 because we are always going away from the center, which is 0. Also, it's a greater sign in our alternative hypothesis, so that usually tends to match. It's a pretty good clue. So here, when I use my TCDF in the calculator, so second vars, number 6 is TCDF. This time I want 1.349. My upper is going to be 100,000, just some giant number. Degrees of freedom here, n was 10 minus 1 would be 9. Paste, paste, paste. So we get 0.105 as our p-value. All right, finally, then our decision, we weren't given a significance level, so we get to choose. Usually this significance level is something that needs to be decided on before you start the test, but also on a test, it should be given to you so that there is no decision that you really need to make here. But we're going to go with 0.15 for our significance level today. So filling this in, we have a p-value of 0.105. This is less than our alpha value of 0.15, so we get to reject. There is evidence that the true mean difference in times, I'm going to shorten this a little bit, is greater than 0. I'm also going to put that we subtracted regular minus express. Wow, I can spell. So that our reader knows this is how we subtracted and that's how we got a positive number. So this means that the express lane is actually faster. But also, this is only on average. So the express lane is faster on average because that's how we calculated this hypothesis test. Everything is dealing with a sample and their averages, so that's why we need to say on average. All right, one last thing that I want to talk about for this section, the very last thing. So I want to talk about the difference between confidence intervals and hypothesis tests. We were saying how they were related before, especially because of that confidence level and the significance level, alpha, and how those correlated with each other. The next thing I also wanted to mention was that in this last problem, we looked at a significance level of 15%. So if we were to draw this out on a normal curve, we would have shaded this direction where the shaded region would have been like where I rejected. If this was 15%, when we make a confidence interval, our confidence interval is usually the percent. The confidence level is what's in the middle, right? So if 15% is out here, then on the other side, there's technically also a 15% over there. So that means the middle percentage would have been 70%. So in our last problem that we did, if we were to make a confidence interval with the same data, using the same significance level, it would have corresponded with only a 70% confidence interval, which is kind of weird because when we think of alpha level of 15% or 0.15, it kind of sounds like the complement of 0.85 should have been the confidence level, but this is not the case when we're looking at one-sided tests. Because of that rejection region where the significance level is, because we're only rejecting on one side, that middle percentage is still different because a confidence interval always includes both sides of the normal curve. However, if we were to look at a two-sided test, let's say the alpha level was 0.15 again, a two-sided test would have included the percentages of both ends of the normal curve, and then both those ends would have needed to be 15% total, so it would have been 0.075 on each side, which then means that middle is in actuality 85%. So that's one thing I wanted to bring up because while the confidence intervals and hypothesis tests are related, their confidence levels and their significance levels are related, the numbers don't always match up depending on what kind of test that you have. So you want to be careful with your hypotheses and looking at which one you have when you are going to also make a confidence level to go with your hypothesis test. All right, this was a really long video. Thank you for sticking all the way through. I would like to offer you some extra credit if you can comment with a smiley face on your notes submission on Canvas, then I will give you some extra credit. Otherwise, if you're not in my class, I'm so sorry, I can't offer you extra credit. Thanks for watching my video though. Don't forget to like and subscribe. Bye.